All right, so this is 11.4. So in 11.3, well, let me give you the title first. This is basically on the cross product. So in 11.3, we talked about the dot product, which was one primary way of quote unquote multiplying two vectors. So the cross product is sort of the other one. These are sort of the two primary ones that we do with vectors. So like a little intro here. We'll say the dot product, which we did. Let's say one of the two primary ways, let's say, of multiplying, in quotes, two vectors. The other is the cross product. So before I give you the definition of the cross product, there are a variety of ways to define this, but notationally, there's a way that we could do it which makes it sort of easiest to remember. So let me sort of start with a preliminary definition. It's really sort of a preliminary notation. So what it can help to do is, so what I'm going to do is I'm going to give you the notation for the determinant of a 2x2 matrix. And if you're taking linear algebra, that will make sense to you. If you haven't, it doesn't matter. The key thing to remember is when you see some notation, which I'll give you, is you want to do a calculation. In other words, when you see the notation, so it looks like an absolute value with 4 numbers in it, like this. Right? You want to replace this by AD minus BC. So it's the product of the upper left and the lower right minus the product of the other two. So for example, if you see, say, 1, 2, 3, 4, you would replace that by 1 times 4 minus 2 times 3. That's 4 minus 6 is negative 2, and that would be the number that you would get. So, like I said, this is the determinant of a 2x2 matrix. If you know that from linear algebra, great. If you don't, doesn't matter. But this allows us to write the dot product in a way that makes it easy to remember. Right? So now we can define the dot product. So given two vectors, so I'm going to write these one above the other, and you'll see why in a second. So vector A will be A1I plus A2J plus A3K, and B will be B1I plus B2J plus B3K. Then we'll define the cross product. This is also sometimes known as the vector product. We'll say AKA the vector product. The reason for this, of course, is it's going to give us a vector. And so this is what we do. The notation is looks like a multiplication, like a cross. Right? So this is the way it works, is I'm going to construct a vector. And for the I component, I'm going to do one of these little determinants, like you see on the left. And so for the I component, what I'm going to do is I'm going to look back at my A and my B. I'm going to ignore the I's. And I'm going to look at the numbers that remain. So A2, A3, B2, B3. So take a second to see what's happened there, right? So I'm building the I component. So I cover up the I components in the A and the B. And I take the other 4 numbers and I just slot them in. A2, A3, B2, B3. Then I do a minus. Then we do another one, and you can possibly see what's about to happen. So for the J, I ignore the J components of A and B, and I fill in the remaining numbers. So A1, A3, B1, B3. And then we do a plus. So the reason for the plus minus plus is buried deep within theories of linear algebra here. We do a K component. It's a terrible absolute value. Let me fix that. And then for the K component, we ignore the K's and we do A1, A2. B1, B2. Now, for what it's worth, according to this little notation on the left that we did right here, you can then work this out, right? You can write this as A2B3 minus A3B2I. You can write this next one as A1B3 minus A3B1J. And you can write the third one as A1B2 minus A2B1K. Now, this is what the book does. In fact, the book takes this middle one right here and it distributes the negative sign. So this could actually be written as plus A3B1 minus A1B3. Here's the problem, is that this calculation, let me circle this form right here, at least for me, this is hard to remember. For me, if you can remember it, if you can memorize it, hey, have at it. Like, good luck to you. I can't, right? So generally what I'll do is I'll just look at this. This is the one I'll remember right here, up here. And then I'll just do this calculation as needed every single time. And you don't even necessarily need to write this notation every single time, as you'll see when we start to go through, right? So, but for the first one at least, I will. So for example, if I write, say, A equals 2I plus 0J plus 5, that looks like a Y right in there, that's a J, it's a bit sloppy, plus 5K, and if B is negative 1I plus 3J plus 4K, then when we do that cross product, A cross B, so this time I'll write it all out with the determinants. So for the I component, I'm going to ignore the I component in A and B, and I'm going to write down the 4 remaining numbers, 0, 3, 5, 4. Do a minus. For the J component, I'm going to ignore the J's in A and B, 2, negative 1, 5, 4. For the K's, ignore the K's, 2, 0, negative 1, 3. And then what we're doing is we're doing the calculation on the left. So 0 times 4 minus 3 times 5 is negative 15I. Minus, so we have 2 times 4 is 8. Minus a negative 5. So 8 plus 5 is 13. J right there. And then 2 times 3 is 6. Don't worry about what this vector represents just yet. Just notice that we did the calculation. Right? Now, if you stop and you think about it, we don't even need to have, this preliminary middle step, right? So let me mess up the picture just a little bit to point something out. Is you'll see what I'm about to do. When we do this calculation, when we do the I component back up in the A and the B, we can do this times this minus this times this. That's the I component. When we do the J component, we do this times this minus this times this. And for the K component, we do this one times this one minus this one times this one. So as long as you remember that, then you don't need to sort of write this intermediate step. But by all means, write however much you need to write for it to make sense. So what we'll do next is similar to the dot product, is I'll talk a little bit about the basic properties, like why do we call this a product, and then talk a little bit about some other properties that it has. Also, it has some perpendicular properties, just like the dot product has, but they're a bit different. So first, the basic ones. So let me clear all this. Actually, let me just clear the left side off, because it'll having the right side will help us see help us see one of the properties I'm about to give. All right, now that I've cleared the screen off, before I give these basic properties, there's one note I want to make about the cross product before I give those properties. And that note is that one thing to realize here is that the cross product, you may have looked at the definition, which is still on the right. You might wonder, like, well, what happens in 2 dimensions? Right? So here's the issue. It's not an issue, it's just something to realize, is that the cross product is a very 3-dimensional thing. And so if you're in 2 dimensions, right? So in other words, if A and B, let's say, are in 2D, then A cross B, the way to think about it, it will, I'll put this in quotes, will sort of pop out into 3D. So for example, let's suppose A is 2i plus 1j, and B is 4i minus 6j. So if we want to do A cross B, we need to augment these. In other words, we need to first add a k component. Basically, the definition requires that I have a k, and so in this case it will be 0 for both of those. So the first thing we need to do is this. Then when we do the cross product, let's see what happens. I'll write this out. So we hide the i's, and we do 1, 0, negative 6, 0. And we cover up the j's, and we have 2, 0, 4, 0, the remaining numbers. We cover up the k's, and we have 2, 1, 4, negative 6. Now if you look at what these turn out to be, the first calculation is 1 times 0 minus 0 times negative 6, that's 0. The next one is 2 times 0 minus 0 times 4, that's 0. We can make a plus 0. And the third one will be 2 times negative 6, which is negative 12 minus 4. That's negative 16. So you can see what happens here is, you start with these two things in 2 dimensions, and the result is all k. Right, there's no i's and j's remaining. So you cannot, for example, take two vectors only having i's and j's and cross them and expect to get something that just involves i's and j's. It doesn't work that way. Like, you need to have 3 dimensions available to do the cross product in any sense. So that's just a note to keep in mind. So let me just make, again, first the basic properties of the cross product. All right, so first off, these are the basic properties. So again, we had this sort of conversation back with the dot product. We asked, why is it called a product? And the answer was, well, because it behaves like a product, behaves like a multiplication. So the same is mostly true with the cross product. There's one slight difference. Right? So I'll list all these things. I'll list the ones that make sense first, and then, or the ones that are familiar, that will be familiar to you, and then I'll end on the ones that are less familiar. Right? So the first one is we get distribution. So in other words, if I have a vector A and I cross that by B plus or minus C, 2 other vectors, I can distribute that multiplication. And I'll put parentheses here just so that we can see what's happened. And this happens whether you cross at either end. In other words, if you cross on the right, you'll get the same thing. You can still distribute. You just distribute the other way. So like multiplication, behaves as you think. Same with if you have a constant. So C in this case without the bar over it is a constant. So if I have C A cross B, I can give that C to either the A or to the B, just like with regular multiplication. Makes no difference. Now, the last one is the one that's a bit more confusing. And so for the dot product, we knew that A dot B and B dot A were the same. For the cross product, they're not. Right? So it turns out that if you reverse the order of the cross, you negate the result. And this happens because of the way that you're multiplying it. If you think about the example over here on the left, if you flip the rows, right, if you sort of reverse these numbers all the way along, you'll get the negative of the result. Like that final one will be 16 instead of negative 16. So I want to emphasize this because this is something to keep in mind. It's sort of the one thing that that makes it a little unusual. In mathematics, if you like fancy math words, this is called being asymmetric. Or rather, sorry, I have that word totally wrong. In mathematics is what's called being anti-commutative. Let me get my phrasing right. So the last one, basic property to give, is if you cross something with itself, you get the zero vector. And that's because you're just sort of multiplying and subtracting the same thing every single time. So, good one to remember. Now, for what it's worth, none of these 5 is necessarily obvious. Some of them are more obvious than other ones, but the cross product is an ugly calculation. And so it's, even something like A in the basic properties here isn't screamingly obvious, right? It's a calculation involved in doing this. So be aware of that. And then 4. I'm going to call these, let's say, let me call these angle properties. And we'll start by saying, suppose that A and B are non-zero vectors. So the first fact is it turns out that if the cross product is 0, although this is an if and only if, so let me say it this way, is that the cross product is the 0 vector if and only if A and B are parallel. So if you remember, the dot product had a similar feature, is that the dot product is 0, the scale is 0, if and only if they're perpendicular. The cross product is 0, 0 vector, if and only if they're parallel. Again, not really screamingly obvious. This will follow from a calculation in a minute, but just to get that one out of the way. A, we won't actually use that much, but A helps us understand B. So B we will use a lot, right? B is probably like the primary use for us of the cross product. And I'm going to emphasize that when we're done here, so just keep it in the back of your head right now. So it turns out that if they're not parallel, in other words, if the cross product is not 0, then the vector you get, A cross B, is perpendicular to both A and B. And in a second, after I give part C, I'm going to draw a picture of this. But before I do, let me really put a big asterisk next to it. Actually, let me box this. This is probably the most important use of the cross product that we have, which is obtaining a vector which is perpendicular to the 2 starting vectors. So there'll be many times during the semester in which the question will arise, hey, you have 2 vectors, how do you get something perpendicular to both of them? And the answer you always want to give is cross them. Like, that's the answer. And we can do an example in a second just to reinforce it and also show you visually what's going on. And C, if you remember with the dot product, the first property that we gave in the perpendicular properties had to do with the dot product and the cosine of the angles. There's a similar one for the cross products. We don't use it that much, but it's worth mentioning. And that is that we have, just so you sort of see the symmetry, see the analogy between them. If you take the cross product and take its magnitude, you get the product of the magnitudes of the vectors times the sine of the angle between them. Again, this is not overly useful for us. It's a useful fact in various places, but for us, not overly useful. And so the one thing I want to emphasize before, there's one last thing I want to give about parallelograms, but the second last thing I want to mention, say something more about, is part B. I want to give you an example of B so that you believe it, and then I want to give you a picture as to what's actually going on so that we visually see what's happening. So let me clear off the left-hand side of the screen, and then we'll focus in on B for a second. So I'm going to call this reinforcement of B. So first I'll just give an example, just so that you believe what's happened. Right? So let's say that A is 2i plus 1j. We'll make these really nice numbers, plus 1k. And B is 3i plus 2j plus 0k. So what I'm going to do is I'm going to first take the cross product. So this is the last time I'm going to write out every gory detail. So the I component, we have 1, 1, 2, 0. For the j component, we have 2, 1, 3, 0. For the k component, we have 2, 1, 3, 2. So here we get 1 minus 2, which is negative 2i. 2 minus 0, minus 3 times 1 is negative 3, but that's a minus, so plus 3. And 2 times 2 minus 3 times 1, this is plus 1. Okay. So now my claim is, sorry, I messed up there. Claim that this is perpendicular. This is a fancy math notation for perpendicular. Claim this is perpendicular to A and B. So how do we check perpendicular? Take the dot product, right? So if I take A and I dot it with this result. All right, so here what I'm doing is I'm going to dot, let me label these, I'm going to dot this guy and this guy. Remember how the dot product works? Dot product, you just multiply the components and you add them. So when I do this, I get 2 times negative 2, not mess this up, plus 1 times 3, plus 1 times 1, and that's 0. And when I check it with B, now what I'm doing in this case, let me use a different color, I'm dotting B up here with this same one right here. So when we dot those, here we get 3 times negative 2 plus 2 times 3 plus 0 times 1. And that is also 0. And this will always work. In other words, the cross product will always, when you dot it with the originals, will give you 0. So now let me just draw a picture of what's happening here. So let's say visually, how does A cross B look, let's say, compared to A and B? So let me do this on the right hand side of the screen. It takes a bit more room than I have down on the left. So let me clear off the right hand side of the screen and give it there. So this is how you want to visualize this. This is not very abstract, but you sort of have to sort of wrap your head around a good three-dimensional idea. So first of all, before I draw anything, I want you to picture that you have 2 vectors A and B. If you anchor those at the same place, they form like a plane. So in other words, this is what I want you to visualize. Imagine like a plane floating in space, just like a rectangle. I can put it at an angle, doesn't really matter. And imagine that the A and the B are in there. So those are lying in the plane and they form an angle theta. This was the angle that came up in one of the properties. And so really think about it the other way around. Think about it, you've got an A and a B and they span a plane in linear algebra terms, or there's a plane that contains them both if they're anchored at the same point, and we can anchor them anywhere. So now what you want to do is you want to think about the right hand rule. So imagine taking the fingers of your right hand and pointing them along the A direction and then curling them towards the B direction. So this would be sort of messy fingers, but that's okay. So picture this, before I draw the thumb, picture this being, let me make the fingers a bit longer. There we go, silly long fingers. Those are kind of going from the A direction towards the B direction. So the A direction is sort of this way, and the B direction is this way. So the fingers are curling from the A towards the B, like this. So then picture which way your thumb goes. In order for you to do this with your right hand, is your thumb has to go like this. So this is your thumb. And then you ask yourself, well, which way does your thumb point? Well, your thumb, it turns out, will point in the direction of A cross B. So on our picture here, this will be our A cross B. And so the perpendicularity is arising right down in the sense that we've got perpendicular here and perpendicular here. It is perpendicular to both of those. So that's where that's arising. But again, the big thing to remember is if you have an A and a B, if you cross them, the result will be perpendicular to both. So, final note. Here's a final sort of interesting, useful fact about the cross product. And that's this. If you imagine taking the vectors a and b, those form a parallelogram. We saw this when we were playing around with what the addition looks like, right? So consider, don't worry about the addition right now, but consider that a and b form a parallelogram. So in other words, for example, here is the A, here is the B. And let me use a different color here to fill in the parallelogram. Parallelogram, you can imagine, is this. Right? So I sort of made a copy of B and a copy of A in order to complete the parallelogram. And this parallelogram has an area right in here. And that area is related to the cross product. That it turns out, and this is basic trigonometry. This isn't difficult to prove. It's related to the sine. It's not hard. So it turns out that the magnitude of the cross product, which was that product of the magnitudes times the sine of the angle between them, this turns out to be the area of the parallelogram. This, we won't use this a whole heck of a lot. The reason I want to give it, so just sort of like dump it somewhere in the back of your head, is that later on in the course when we're playing around with some fairly complicated integrals, magnitudes of cross products will arise. And it can be helpful if you're really interested in the technical details to understand that this represents this area of a parallelogram, because that has an impact upon what's going on with the integrals. So it's a small technical detail, so it's not something to obsess over, but it's a good fact to keep in the back of your head. So that's the last thing then. Cross product is a short topic, so we'll call that done. End of 11.4.